In this video, we're going to have a look at second order homogeneous differential equations. So first of all, let's define what a second order differential equation is. Well, it's an equation of the following form. So we've got a d2y by dx squared plus b dy by dx plus c times y. And what makes a differential equation homogeneous is when the right hand side is equal to 0. So to summarise, what makes this differential equation second order is the fact that the highest order differential here is the second differential. What makes it homogeneous is the fact that it's equal to 0 on the right hand side. So now let's try and go about solving this equation. Well, when looking at this, we want a second order differential plus a first order differential plus the function itself to add together, some multiples of them to add together, and for it equal to 0. Well, a prime candidate for a solution, i.e. something when you differentiate it, it doesn't change, so we could very well have terms cancelling out, would be the exponential function, e to the x, or a multiple thereof. So let's, as a solution, let's try y equals some multiple of e to the power of mx. Well, that means the differential equals m a e to the mx, and that implies that the second differential equals m squared a e to the mx. Okay, so now subbing it back into the original equation, we get a times the second differential, which was m squared a e to the mx, plus b times the first differential, which is m capital A e to the mx, plus c times y, which is a e to the mx, and we know that that's equal to 0. So we've subbed our proposed solution into the original equation. So this implies, if we take out the factor of capital A e to the mx, that a m squared plus bm plus c times a e to the mx equals 0. And now we've got a general form for finding a solution. So we've discovered that this here truly is a solution when these conditions are met, i.e. when that is equal to 0. So we can either have this equal to 0, which can't happen because we know if the function e to the mx is asymptotically 0 and the constant a, unless it's 0, won't let that happen. Or when this equals 0. And this interesting equation here, when we're talking about second order differential equations, this one is called the auxiliary equation, and you need to learn that terminology. So auxiliary equation. So solutions to this equation are of this form when m is such that it solves this auxiliary equation here. So what this also says is that any solutions are independent of the value of this constant a. Because we've taken a outside the bracket, the only thing that it depends on are these constants here, lowercase a, lowercase b, and lowercase c. So what we've discovered here is that any, I'm going to abbreviate, second order differential equation like this, of the form a d2y by dx squared plus b dy by dx plus c equals 0 has solutions a e to the mx, where a m squared plus bm plus c equals 0. And that's a really significant point when it comes to second order differential equations. So let's now try an example question. So we've got this question here, and note we're only going to look at examples in this tutorial of when the auxiliary equation has real and distinct roots. We're not going to look at the complex roots, imaginary roots, or repeated roots case. We're only going to look at the case where the roots are real and distinct, i.e. b squared minus 4ac being bigger than 0. So remember, we just discovered before, any second order differential equation of that form has solutions a e to the mx, where am squared plus bm plus c equals 0. So let's solve the auxiliary equation. So we've got the coefficient a is 1, the coefficient b is 1, and the coefficient c is minus 6. So we've got m squared plus 1m take 6 equals 0. So solving that, m plus 3, m minus 2 equals 0. Therefore we've got m equals minus 3 or m equals 2. That means that our solutions, y equals a constant times e to the minus 3x, or y equals a constant b times e to the power of 2x. Both of those are valid solutions. However, because of the linear nature of the differential operator, it can also be a combination of the two. So a e to the minus 3x plus b e to the 2x. And typically, we don't write this line here. It's accepted that we just do the linear combination of the two. So mathematical convention states that if you write this, you mean a linear combination of the two solutions is a solution, or each individual one is a solution as well. So you might or might not be interested in me proving this, but I'm going to do it anyway. So I'm going to prove that each individual solution, i.e. this one here and this one here, are each solutions. Then I'm going to prove that they're both solutions in a linear combination as well. So let's say if y equals a e to the minus 3x, well, that means that dy by dx equals minus 3 a e to the minus 3x, and that implies that d2y by dx squared is equal to 9a e to the minus 3x. So now let's sub that into the original equation, which implies, so we've got d2y by dx squared, so 9a e to the minus 3x plus dy by dx minus 3 a e to the minus 3x, take 6y, so take 6 a e to the minus 3x equals, let's count these up, so we've got 9 lots of this, take 3 lots of this, take 6 lots of this, which indeed equals 0, as we expected. Let's make that look more like a 0. There we go. Right, let's do it for y equals b e to the 2x. So y equals b e to the 2x, which means that dy by dx equals 2b e to the 2x, which means that d2y by dx squared equals 4b e to the 2x. Sum it into the original equation. Let's just put it there in green to remind ourselves what it is. So d2y by dx squared, so 4b e to the 2x, plus dy by dx, so plus 2b e to the 2x, take 6y, so 6b e to the 2x. Let's count them up. So we've got 4 lots of this plus 2 lots of this, take 6 lots of this, which truly is equal to 0, as we expected. So yes, that's a solution. So now what I want to do is justify why a combination of the two is a solution as well. So let now y equal a e to the minus 3x plus b e to the 2x. So that implies that the differential, the first differential, is minus 3a e to the minus 3x plus 2b e to the 2x. And that means that the second differential is equal to 9a e to the minus 3x plus 4b e to the 2x. So now let's sub it into the equation, which I've put there in green to remind ourselves of what it is. So d2y by dx squared. So 9a e to the minus 3x plus 4b e to the 2x plus dy by dx. So take 3a e to the minus 3x plus 2b e to the 2x. Take 6y, so take 6a e to the minus 3x, take 6b e to the 2x, and we've got exactly the same thing again. All the terms just appear separately, so because the differential operator is linear, we can just gather up the terms that we want. So there, we can see that equals 0. We can see that those ones add together to make 0. So what we've done is just justified that the combination of the two solutions is also a solution, but all we need to write to get the marks is y equals a e to the minus 3x plus b e to the 2x, where a and b are arbitrary and independent constants. For more videos like this, subscribe to our YouTube channel, and to find out more about our Skype tuition and revision courses, go to alevelmathsrevision.com.